So here's a typical 2 degree of freedom system. We've got two masses, M1 and M2. Okay, we're connected with springs, K1, K2 and K3 with dampers, C1, C2 and C3. Okay, and mass 1, we've got a motion that's given by X1, okay, and there may be a force being applied to mass 1 called F1, and the same for mass 2, you've got X2 and F2 being applied to those masses. And if we apply Newton's second law, it's quite clear that mass times acceleration is the sum of all the forces. Well, the only force that's in the same direction as x is the applied force, F1, and all the other forces, the damping forces and the spring forces, are opposing it, hence the minus signs here and here and here. Now, C2, okay, is the damper that's between the two masses. If I go back to the picture, you can see that C2 is between the two masses, and we know that damping and the spring force of K2 is based upon the relative velocity for the damper and the relative displacement of the spring. And so when you've got these the equations, you can see quite clearly that instead of this just being C2 x1 dot, we've got to take the relative velocity, so x1 minus x2, x1 dot minus x2 dot, multiplied by C2. And over here we've got the same thing with the spring, okay? And so what I've done in this line is I've just rearranged it. I've put all the terms with x in, and x dot in, over onto the same side as the mass times acceleration. Okay, so all those minuses become pluses over here. Okay. And I've multiplied out some of these terms. So I've grouped them in terms of x1 dot, x2 dot, and x1 and x2. Okay. And then obviously F1 is on the other side. You can repeat the process for the second mass, okay? And now obviously we've got the relative velocity, but this time it's x2 dot minus x1 dot. Notice that it swaps. You start with the term that you're referring to, okay? So here we've got x1 dot minus x2 dot, because I'm dealing with x1. Here we've got x2 dot minus x1 dot, because I'm dealing with x2, okay? And so you do the same thing again, and obviously down here we've got the, we've got C3 as well, so there's a C3 term, and K2 and K3. So those are two equations, this one here and this one here. And what you can do is you can convert that to write that in what's known as matrix form, okay, which looks like that. And so if you multiply this matrix out, you get M1 times by x1 double dot, okay, and then plus C1 plus C2 times x1 dot minus C2 times x2 dot, and then K1 plus K2 times x1 minus K2 times x2 equals F1. That's the first equation. The second equation is basically the second one. Okay. And this can be represented with this by this method, where big M in square brackets is the mass matrix. We've got C in the square brackets, which is the damping matrix, and then K in the square brackets, which is the stiffness matrix. F in curly braces is the force that's being applied. Okay, and x in curly braces, and x dot and x double dot represents the displacement, velocity, and the acceleration respectively. And this will always be the case for a linear system. Okay, if your system is linear, you should be able to write it in this form. Okay, where you have a mass matrix, a damping matrix, and a stiffness matrix. If our forces are 0, then obviously it's exactly the same equation, but instead of F1 and F2, we've got 0 in there, and that makes sense. Now, this is new. You won't have covered this last year. There is a quick method that will allow you to fill up those matrices. So if I give you quite a complicated system and say, what's the equation of motion, okay, in matrix form, there's a quick method you can apply that will quickly allow you to fill up those matrices so you've got your equations of motion. You don't have to go through Newton's second law and finding mass times acceleration and then applying all the forces, working out what the forces are between, say, mass 1 and mass 3 and so on. There's a quick method you can follow. And these are the rules that apply. J and I are just basically indices of the matrix. Okay, so the first box in a matrix in the upper left-hand corner would be M11, or for the mass matrix, M11. Okay, and obviously in the bottom corner would be M33 or M22 or whatever. Okay, so that's MII, and that just equals mi. So in the first box, m11, that just equals m1, the first mass. And in the second one, m22, that would just equal the second mass, and so on. Anything that's not on the diagonal, so mij, okay, so m12 and m21 will be 0. So basically your mass matrix is just the diagonals, okay, and you simply list the masses that are in your system. Okay, m11 will be m1 and m22 will be m2. That's exactly what. And anything that off diagonal, which is given by the ij, because they're not equal to each other, will equal 0. There's the mass matrix, straightforward. Now for the damping and stiffness matrix, it's a little bit more complicated. For the diagonals, okay, so CII and KI, what you do is you take your mass and you look at all the springs that are connected to that mass. So connected to either ground or to another mass. And you add them up, okay, you sum them, okay, all the dampers that are connected to that mass, you add them up, and that will be on your diagonals. So for C11 or K11, you look at, for K11, you look at all the, take X1 and you look at all the springs that are connected to it and you just add them up, and that will be what's in the diagonal, okay? For the first mass, it will be K11 and the second mass will be K22. And the same for the dampers, okay? So the sum of all the springs and dampers connecting the mass to either ground or to another mass. For the off diagonals, what you do is you take the minus, okay, the sum of all the springs and dampers connecting mass I to mass J. Okay, so if we had a 2 degree of freedom system, C12 and K12 is minus the sum of the springs and dampers connecting those two masses together. If you have a 3 degree of freedom system, then obviously you've got 1, 3 and 3, 1 and 2, 3 and 3 and 2, 3 and 3, 2, and they will also be the same thing. So if I had a 3 degree of freedom system and I'm looking at the spring connecting mass 2 to mass 3, then obviously this would be K23, so second row, third column, okay? And that links mass 2 to mass 3. Is that a question? Are you stretching? Okay. So, diagonals is the sum of the springs and dampers connecting M1 to ground or to another mass, okay? And the off diagonals is minus the sum of the masses connecting the masses, it's the sum minus the sum of the springs connecting those masses together, or dampers. And that builds up your M, C and K matrices. And for a linear system, those matrices will be symmetrical, okay? Symmetrical, what we mean by a symmetrical matrix is a matrix where you can reflect it about the diagonal and you get the same thing, okay? So that's why C12 will equal C21, okay? First row, second column will equal second column, first row. So first row, second column will equal second row, first column, okay? So that's what we mean by the fact that they're symmetrical.